Hello, everyone. This little video is to tell you about one of my favorite things in discrete math, which is combinatorial proof. I want to start off by telling you a few cool facts about the binomial theorem. And before I do that, I want to motivate where it comes from. So what we have here on this page are two binomials. It's a binomial. X plus y is a binomial because there are two terms, an x plus the y. And when we multiply it out, of course, what we really have, x plus y squared is the quantity x plus y multiplied by itself. And when we multiply it out, what we do is we're using the distributive law. And first, we're going to multiply this x times this x and that y. So we get an x squared plus an xy. And then we take the y and we multiply it by that x and that y. So we get yx plus y squared. And then because x and y commute with each other, we can combine this to get x squared plus 2xy plus y squared. Okay? And then we look at this and we can think, wait a minute, there's a counting way to figure out how many of each different term I'm going to get. For example, when I multiply this out, I'm going to get an x squared term. How many of them do I get? Well, what you can see is to get that x squared, I need to pick an x from the first factor and an x from the second factor. So I don't really have any choices to make. There's only one way to do that. And that's why I only have one of the x squareds. However, when I want to try to make the term xy, I can do it by picking an x from the first factor and a y from the second factor, or vice versa. So there are two ways of doing that. And then finally, when I want to find the y squared, I have to again pick the y from both factors, right? So then there's only one way of doing that. It's very similar when I expand out x plus y cubed, then I get x plus y times x plus y times x plus y. And we can think about what kinds of terms am I going to get? Well, I'll get an x cubed, and there's only one way to do that. I have to pick the x from each of the three factors. So I get x cubed. And then how many ways are there of getting x squared y? Well, let me think about this now. I'm actually going to think about this, instead of choosing x's, I'm going to think about choosing y's. So for the first term, I chose 0 y's. For this term with x squared y, I'm going to choose exactly 1 y, and that can be from any one of the three factors. So I'm going to think of this as 3 choose 1. And for the first time, I had three factors and I chose 0 y's. For the second one, I have xy squared, and now I have to pick 2 y's from among these three factors, three factors, right? So it'll be 3 choose 2. And then how many ways can I get a y cubed? I have to pick all the y's. So I have 3 factors and I have to pick 3 y's. And what you can see, if you do use the distributive law carefully, is you will get x cubed plus 3x squared y plus 3x y squared plus y cubed. Okay? All right. So those examples help us to see why the binomial theorem holds in general. In general, we have x plus y to the n is x plus y times x plus y, where I multiply x plus y, n copies of them. So these are n of them. And then I can think, well, how many ways are there to get an x to the nth? Well, I have to choose no y's from any of the factors. So I have n factors and I'm choosing 0 y's. In how many ways can I get the term x to the n minus 1 times y? I still have n factors. Oops, I still have n factors, and now I have to choose just one y from them, etc. Until finally, at the end, I have things like x times y to the n minus 1, where I have to choose n minus 1 y's from my n factors. And finally, to get a term like y to the nth, I have to choose n y's from the n factors. And just remember that n choose 0 is equal to n factorial over 0 factorial times n factorial, which is 1. This is also 1. This is n, etc. Okay, so that's the binomial theorem. Let's see how we can use it in some pretty cool ways. For example, suppose we have this sum, which holds for every n greater than or equal to 1, that n choose 0 plus n choose 1 through n choose n is equal to 2 to the n. So here's a cool way to see that it's true. So here's a binomial theorem proof. Well, what we can do is let x equal to y equal to 1 in the binomial theorem. So what happens then? Well, in the binomial theorem, we had that x plus y to the nth is supposed to be equal to n choose 0 times x to the n plus n choose 1 x to the n minus 1 y plus through n choose n minus 1 x to the x to the first y to the n minus first plus n choose n y to the n. But what we see is that 1 plus 1 is 2 on the left-hand side. And on the right-hand side, all those powers of 1 are just 1. So I really do have my sum n choose 0 plus n choose 1 plus dot, 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 plus n choose n minus 1 plus n choose n. And that's exactly what I wanted to show. I didn't have to use some induction proof. I didn't have to get into that formula with the factorials in it. Pretty neat, huh? We can also use the binomial theorem to compute a kind of complicated sum like the one at the bottom in the example. So let's see what this really is. Maybe we can write this out a little bit. So it's like -1 to the 0, n choose 0, 10 to the n, plus -1 to the first, n choose 1, 10 to the n minus 1 plus, I'm going to try to get it in here, -1 to the n, n choose n, and I'm, ooh, that was weird. And it's 10 to the 0, so I'm not going to write it because 10 to the 0 is 1. Okay, well, what is this here? Let's let, if we want x equal 10 and y equal -1, then by the binomial theorem, so in the binomial theorem, then what we have is 10 minus 1 to the nth is equal to this terrible looking sum. I'm going to write it like this. K equals 0 to n, -1 to the k, n choose k, 10 to the n minus k. And what we see then on the left-hand side is this is just equal to 9 to the nth. Pretty cool. Do we believe it? Like, let's do one of them, maybe for n equals 2. Well, let's do n equals 0. Like when n equals 0, what do we get? We'll just get the -1 to the 0 times n choose 0, which is 0 choose 0 times 10 to the 0. That's all equal to 1. And 9 to the 0 equals 1. You can also maybe try it for 9 to the first, for when n equals 1, to make sure you really believe it. Okay, so this is really my favorite thing in discrete math, is combinatorial proof. And so if the principle here is you can prove two complicated formulas are the same by just showing that they count the same set, which is pretty cool. So like we can use a combinatorial argument to show why n choose n minus 1 is equal to n. So without that formula with factorials, why, so let x equal a set with n. If x is a set with n elements, then n choose n minus 1 counts the number of n element subsets. But we can also pick n minus 1 element subsets by choosing which one element to leave out. So we can also count the n minus 1, oops, this should be n minus 1 element subsets. Instead of sort of positively picking the n minus 1 elements to take, we can negatively choose the one element to leave out. And there are n elements in the set, and I can leave any of them out. There are n elements to choose to leave out. What else can we use a combinatorial proof for? So this is my favorite one. Why is n choose k the same as n minus 1 choose k minus 1 plus n minus 1 choose k? Well, here's a proof. So let's think. Suppose x is equal to a set of students in our class, and we want to count subsets of k of them. So what we're going to do is we're going to designate one special student. Suppose one student has a purple hat, and we'll call this student P. Okay, well, so then I can say there are two cases. P is in this k element set, or P is not in this k element set. Well, how many ways can I choose a set of k that has the purple hatted student in it? Well, there are n minus 1 students who are not student P, and I have to choose k minus 1 more of them to get a full set of k, including P. And then I can think, well, what if P isn't in a set? Well, then I have to choose K students from the n-1 students who aren't P. And so that's why if I'm trying to choose a set of K students from a class of n, there are n-1 choose k-1 plus n-1 choose k ways to do it. All right, and that is it for now. Thank you.